So here's a pair of matrices. If I want to take the product of these two matrices, then my question to you is, should I multiply A times B, or should I multiply B times A? Or are they both okay? B times A. Let's write that. So B times A is 1, 1, 1, and 3, 2, negative 1, times 1, negative 1, 0, 2, 3, 1. Okay? So to find this product, what do I have to do? Go across the row of the first matrix and down the column of the second matrix, and that's going to give me each of the entries of their product. So this first entry of the product is going to be 1 times 1 plus 3 times 2. So the first entry in the product of these matrices is 1 plus 6. We'll make that into a 7 in a second. Now for the next entry, we'll use the same column, but a different row of the original. And go again across the row and down the column and multiply and add. So 1 times 1 plus 2 times 2 will give me the next entry in this product. And then take another step down the row of the first matrix to get our final product in the first column of the product. 1 times 1 plus 1, negative 1 times 2. And there we have the first column of our product. The first column of the product came from the first column of the second matrix, multiplied into the first, second, and third rows of the first matrix. And then, of course, we can keep going. In order to find the next column, we just have to move a column over in our second matrix and then do the same. So here we're going to have 1 times negative 1 plus 3 times 3. And then we'll move a step down and do 1 times negative 1 plus 2 times 3, negative 1 plus 6, and finally move one more step down and do 1 times negative 1 plus negative 1 times 3, negative 1 minus 3. And last but not least, the final column, 0, 1. So here we'll have 1 times 0 plus 3 times 1. And that's just 3. We'll have 1 times 0 plus 2 times 1 from the second row here. So, whoops. When I multiply this one by that one, I'm going to get 2 times 1. And finally, the last row, last column product is going to give me negative 1. Ugh. So one of the things you notice about matrix multiplication is it takes a lot of arithmetic. A computer scientist would say it's an order n squared algorithm. We need to compute the product of every entry of the first matrix by every entry from the second matrix. So they all get paired up one with another by the time we're done. Let's reduce this down. 1 plus 6, 1 plus 4, that's 5, 7 and 5. 1 minus 2, negative 1. Negative 1 plus 9. Negative 1 plus 6. Negative 1 minus 3. And there's the product. By the way, what size is this product as a matrix? How many rows, how many columns? 3 by 3. How could we have known that without having to do all this computation? At least if we wanted to know the size of the product. What was the dimension of the matrix B? How many rows, how many columns? It had it has 2 columns. Yeah, I always get those backwards too. It has 2 columns and 3 rows. So that makes B a 3 by 2 matrix. And A has 3 columns and 2 rows. So 3 by 2 multiplied by 2 by 3. So how could we have known what size, what dimension our product had? Where do we get 3 by 3 out of this? Yeah, these ones in the middle we forget about, and we get 3 by 3 for the dimension of our product. So the product is 3 by 3. And the ones in the 2's in the middle get so-called, crossed out. We can kind of forget about them. But what else is important about this? Can I multiply these matrices in the other order? Can I do the product A times B? A is 2 by 3. B is 3 by 2. How do I know I can do this product? Right, because these dimensions in the middle are the same. Remember when we talked about matrix vector products? In order to multiply a matrix A, which if we think of this matrix as having some columns in it, right, call them A1, A2, up to AN. If I'd like to multiply this matrix by a vector, then how many components must this vector have? N. In other words, there has to be the same number of rows in my vector, which I'm going to think of as an n by 1 matrix. I have to have the same number of rows here as I have columns over here. That these have to be equal. Otherwise, this product makes no sense at all. Because we would be asking to take a linear combination of a set of vectors where we don't have the same number of coefficients as we have vectors. So that we either have too many vectors and so some have no coefficients, or we have too few vectors and so we have too many coefficients to go around. In order to form this product, we needed to have the number of columns of the matrix equal the number of rows in our vector. And because matrix multiplication is built on the same stuff, that still needs to be the case. Then in order to multiply a matrix by another matrix, we need to have the same number of columns in the first one as we have rows in the second one. And in this example, because A and B have just sort of opposite numbers of rows and columns as one another, it means we can do the product in either order. But what can we say about whether or not these products are equal? We know that, we said that in general it's not, matrix multiplication is not commutative. But how can we be absolutely sure that these products are different? Yeah. BA was a 3 by 3 matrix. AB is a 2 by 2 matrix. So even if we didn't know anything else about matrix multiplication besides how the dimensions work, we would know for sure that it's going to matter big time when we multiply matrices in an opposite order. Because even just multiplying them in the opposite order in this example gives us matrix products that have different size. And so we can't have a 2 by 2 matrix and a 3 by 3 matrix equal to one another.